Let's do one more example of the computation of a definite integral using summation notation in Riemann sums. Now, I don't want you to get the wrong idea that people are going and using this method and this technique for all sorts of definite integral problems. There are only a few problems that are even easy enough to do this way. But luckily, some powerful theories on the way that will help us compute definite integrals with ease. So in this example, let's compute the integral from a to b of x squared dx. So here we have, here's the graph of x squared, and we go from a to b, and we're actually computing the area under the curve of y is equal to x squared from a to b. In the previous example where we looked at y is equal to x, the area under the curve was just the area of a trapezoid. So we didn't need to use all this fancy Riemann sum stuff to figure out the area. So you might say, well, why go through all that? Well, here I think that you're going to be hard-pressed to find a simple way to figure out exactly how much area is underneath the graph of y is equal to x squared from between any 2 points, for example, between 1 and 7. How much area is under the graph of y is equal to x squared between 1 and 7? Well, that's probably a difficult question to answer without calculus. So as is normal, we have to set up delta x. So this is just going to be b minus a over n. And then x sub I is a plus I delta x, just as usual. And we'll use a right-hand Riemann sum again, except this time f of x sub I isn't equal to x sub I, it's equal to x sub I squared. So x sub I squared is a plus I delta x squared. So we get a squared plus 2ai delta x plus I squared delta x squared, which is equal to a squared plus 2ai. Now delta x is b minus a over n, and then plus I squared times b minus a squared over n squared. In fact, we can even just leave the delta x in for now. It might be a little bit simpler. So the Riemann sum, right-hand Riemann sum with n subintervals, is the sum I equals 1 to n of this f of xi all times delta x. So it's a squared times delta x plus 2ai delta x squared plus I squared delta x cubed. So that is the formula for the Riemann sum. This is basically the area of the ith rectangle. So the ith rectangle might be something like this, and this gives you a formula. If you use n subintervals, this will be the area of your nth rectangle, right? So delta x is the same delta x as normal. X sub I are the same notches. F of x sub I just took the formula for x sub I, and I place it in for f of x. So f of x is equal to x squared. So f of x sub I is x sub I squared. So we take the formula for x sub I, insert it into x, so we square it. We've expanded that out. We got a squared plus 2ai delta x plus I squared delta x squared. Multiply the whole thing by delta x, and there you go. That's the area of your rectangle. This is the height of the rectangle, and delta x is the width. Next, we have to sum it up. So we can actually use some of our summation formulas when we talked about summation notation to actually sum this thing. So the right-hand Riemann sum with n subintervals, the first term is a constant with respect to I. So I goes from 1 to n, for the I is the index of the summation. There are no i's in the first term, so we just multiply that by n. So it's a squared n delta x. And then plus, we get 2a delta x squared times, the relevant part here is just I, times the sum of I. Now when I sum I from 1 to n, I get n minus 1 over 2. Actually, n plus 1 over 2. So this part here just represents the sum of I from 1 to n. And then the final term, I get delta x cubed times the relevant part here is I squared, so times the sum of I squared from 1 to n. Now when I sum I squared from 1 to n, the formula is that we get n plus 1, 2n plus 1 over 6. So that's the formula for the sum of I squared from 1 to n. It's right here. So there's a nice closed form solution for the right-hand Riemann sum with n subintervals. So all we have to do next is take the limit as n goes to infinity. And we want to be careful because delta x now depends on n, so we better write out what delta x is. So the integral from a to b of x squared dx is going to be the limit as n goes to infinity. So we get a squared n b minus a over n plus 2a b minus a squared over n squared n plus 1 over 2, and then plus b minus a cubed over n cubed n plus 1, 2n plus 1 over 6. And we take the limit as n goes to infinity. Well, for the first term, we basically just have n over n, which is 1. So the first term just gives us a squared times b minus a. The second term, all right, well, the important part here is n plus 1 over n squared. So that, as n goes to infinity, just approaches 1. So again, we can cancel out this n with the squared, and it's just n plus 1 over n. That approaches 1 as n gets large. So it's 1 times everything else. The 2's also cancel out. So we get plus a b minus a squared. And then plus this last term, the relevant part here is n times n plus 1 times 2n plus 1 all over n cubed. So we can cancel this one out, and we can change that cubed to a squared. So when we take the limit as n goes to infinity of n plus 1, 2n plus 1 over n squared, we have a quadratic function of n in the numerator and a quadratic function n in the denominator, so the limit exists, and it's just equal to the ratio of the leading coefficients. Now, the leading term in the numerator is going to be given by n times 2n. n times 2n is 2n squared. So the leading coefficient in the numerator is 2, the leading coefficient in the denominator is 1, the ratio is 2 over 1, so the limit is 2. So that limit is actually equal to 2. So we get plus b minus a cubed over 3. So the 2 over 6 becomes 1 over 3. So that is what the integral from a to b of x squared dx is equal to. Now we can actually simplify this sum. So this is the same as a squared b minus a cubed plus, now when I expand b minus a squared, I get b squared, so that's ab squared. And then I get minus 2ab, so that's minus 2a squared b. And then I get plus a squared, so that's plus a cubed. And then I get plus b cubed. This is all over 3. So I get b cubed plus 3ba squared minus 3b squared a plus minus a cubed all over 3, just like that. So that's what happens when we expand it. So let's get a little bit more space up here. Okay, so we have this expression for the integral from a to b of x squared. We have all this algebra here. Well, let's do a little simplification. So a squared b, let's see, is there anything? Here we have an a cubed. So a cubed and minus a cubed. A squared b, so we have a squared b minus 2a squared b So a squared b minus 2a squared b just becomes minus 1a squared b. Now notice we have minus a squared b, and then over here we have 3a squared b over 3. So this minus a squared b and this a squared b 3 over 3, this one cancels with this one right here. And then similarly we have ab squared and we have minus 3b squared a, or ab squared. So 3ab squared over 3, this one right here, this negative one, cancels with this one right here. So the whole thing in the end is just equal to, we have the integral from a to b of x squared dx is just equal to b cubed minus a cubed over 3. So a nice simple formula. So earlier I suggested, well, what happens if we have the graph y is equal to x squared? What's the area between 2 points? So maybe between 4 and 7. So the height at 7 would be 49 and the height at 4 would be 16. Well, you would do 49 cubed minus 16 cubed over a, and that would give you the area underneath the graph. So pretty amazing technology. I mean, it's a little bit complex here, but straightforward at the same time once you get used to just handling all the notation and all the symbols, to get a formula for something like the area under the graph of y is equal to x squared between 2 points. So it's a fairly interesting formula.